Okay. Good afternoon. My name is Francisco González. I'm going to present the results on the Galileo mission. This presentation is a collaboration between ISA in the Netherlands, ISA and ISA ESOC in Germany, and also my colleague Michael Steindorfer from the Austrian Academy of Science. Let me give you an overview of the presentation. First, I will present the ILRS support status, what is the space segment of Galileo, and the support we are getting from the ILRS. And then I will go through the different results that have been achieved in the last 3 years. And finally, I will talk about the future of SLR in navigation in Galileo. First, what is the space segment of Galileo? There are 2 satellite families. First one is IOB, the second one is FOG. I like these 2 pictures of the Galileo satellites because they show the retroreflector panel. Normally, they are very difficult to be visible. Only when the satellite is going to be integrated into the launcher, the cover of the retroreflector is removed, and you can see the reflector in the pictures. On the left side, we can see the IOB panel being integrated in Sojuz, and on the right side, we can see the FOG satellite being integrated into Ariane. The 2 panels are different. The IOB panel is larger than the one of FOG. They have different characteristics. They have also different optical cross-section. For those not so familiar with the optical cross-section, you can look into the optical area. The optical area, it is almost double in IOB with respect to FOG. There are 28 satellites in orbit for Galileo. 4 of these satellites has been selected by ILRS to be in the priority list. There is 1 satellite per plane that has been selected, and from the 2 families, we have selected 1 IOB. The rest need to be tracked with a low priority, and predictions are provided to all operational satellites. What is the number of normal points ILRS is providing for Galileo? We have processed the normal points from 2018 to today, and we see that there are between 100 and 300 normal points per day. These normal points per day are changing by campaigns. There have been different campaigns in the last year. There were 2 large campaigns to GNSS. There was a success campaign looking onto 2 satellites in eclipse period. There was also a small campaign with our colleagues from Graz looking to symmetry conditions and to long passes. A very interesting campaign last year was Gaston, because this increased significantly the number of normal points from 300 up to 700 normal points per day, with 2 main station contributions that were from France and Jagaradi. The normal points per family is different. For looking into the number per satellite, we have looked into 2019 and 2020. We see that the full rate for IOB satellites for a selected number of 6 stations is higher for IOB than for FOG. You can see here on the left the full rate. On the right, the normal point. The ratio for the full rate is about 0.5. If we look into the normal point, this ratio is slightly improved to 0.7, but clearly shows that there are more data for IOB than for FOG. This was based in 2 years. Then we come back to our colleague from Graz and asked to Michael to look deeper into this. And then he computes the normal points per day from the first launch from 2012 to 2022. Derivated the normal point per day for IOB and FOG satellite. And this seems a different value for IOB and for fog. It is mainly coming from the optical cross-section. Following Michal, it is more difficult to find fog satellites, particularly during the daylight. Optical cross-section plays a role, and we have been looking a little bit more into this. What is the optical cross-section in orbit? For that, we have used a statistical method that was proposed by Lucas in 2001 to validate the retroreflector optical cross-section in orbit. We have the manufactured value, but when we have it in space, we don't know if this value is aligned or not. Then what we have done is to take the IOB values as a reference, as calibrated by ENFM, and fixing that, you can use this method and recompute the optical cross-section of fog satellite in orbit. And using 3 stations, we see that the value is quite well aligned to the specification of 72 million square kilometers. If we apply this technique for Etalon and Lagios, while we get a good agreement for fog, we see that the values for Lagios are significantly lower. If we were expecting a value of 7, the value we observe with this methodology for Lagios and Etalon are 2 for Lagios and around 40 to Etalon. And we have to look more into this. What is the normal point RMS? The normal point RMS at formation depends on the geometry, as Michael was talking about this morning. If the panel is not perpendicular to the observation, we see that some reflectors are closer to the station, some reflectors are farther away of the station, and that is having an effect on the RMS of the normal point formation. We can see clearly that from the expected value if we look into the ILRS information provided on the website. We can see on the left that for satellite 102 for Graz, the values at very low distance, the lower distance are around 3 millimeters. That is quite well aligned with the expected value. And when the distance increases due to the panel inclination, this RMS is also increasing. The same for fog satellite. One example to 10 on the right. In the middle, this is giving a lower value in average for fog, thanks that they have a lower optical cross-section, but they are a smaller retroreflector. Then you get a 10 millimeter with respect to the 15 millimeter of IOB. But this is not the real normal point accuracy and precision. That the normal point accuracy and precision is normally derived from orbit determination. For Lagios, you were showing in different presentation this morning a few millimeters. That is not the same for GNSS, that from the first launch of Galileo, the residual have been improving. They have been a decrease of the residual over time. First, this is due to the force model use. First, we started with Econ 1. Then this was changed in 2016, WICO 1873, with the introduction of Econ 1 plus Boxwing. And there was a second further improvement of introducing phase center offset for calibration for the ground stations, leading to a current precision accuracy of a few centimeters. Orbit model play a role, and for that, to see what is the effect, we have taken the campaign of Gaston, where there were a significant number of laser observations, and trade off 6 different force models. What we can see is that the force model play a role on the mean. That is, depending on the force model you use, there are values that are between 20 millimeters plus minus. On the other side, the sigma After we have using box width model, there is very small difference between 50 millimeter and 60 millimeter of the model. Only if we go to long predictions, normally for GNSS, the orbit determination is done with 1-3 days, in contrary to LAGEOS when you have largest orbits. If you go to prediction up to 14 days, then you see here in meters, there is a clear benefit of using a new box width model for the satellite. Then sigma, it is 50 millimeters for the latest model. This is taking all the SLR stations. If we take only the core stations and then we look into the new station from Itzania 1, it's a Tenerife station, we see that the precision it is up to 10 millimeters. But an accuracy of for Itzania 1 was a mean of 32 millimeter. But from this 50 millimeter and this mean offset, what is coming from the orbit, what is coming from the station, to understand better the station contribution, we have performed a single difference between Itzania 1 station and other stations. Single difference, for single difference, you need a common view between one station and another station, and consider measurements that are within 3 minutes simultaneously. If you compute then the single difference between the other Itzania station and other station, you can see that the orbit contribution disappear. And we see that between Itzania 1 and Betzel, the single difference are showing us a mean in the millimeter range with a precision also in the 3 millimeter range. Same between Itzania 1 and Graz. If we now check Itzania 1 and Potsdam, there is a bias between these single difference that are in the 3 centimeter range. Then this is into the normal point accuracy and precision. I want to highlight that the improvement in some of the improvement that we have done in the orbit modeling were only possible thanks to SLR. One particular improvement was the introduction of a thermal model in the box wing. In orange, this has been also presented for LAGEOS in this one presentation yesterday. There is the thermal environment of the satellite has a contribution on the force. The difference for the Galileo or for GNSS is that you have thermistors and readings of the satellite, and then you can derive with this temperature reading a thermal model. In orange, you have here the a priori effect, and in green, you have the derived computed force empirical, but it's stopped at some point. And here is when the laser plays a significant role because the element was switched off, but with the laser, it was possible to see how this effect was changing over time and validate the value of the normal mode operation and use this 240 watts for force modeling. And this has an implication that are explained by my colleague Florian Disner in another presentation this year in the EU. Finally, talk about future launch. There are 28 satellites of the Galileo in orbit today, but there are still 10 satellites pending launch. These are from the GSAT-02 family, FOC. And also there are new satellites from the second generation being designed and being in the design phase. There are 6 satellites from Thales and other 6 satellites from Airbus to be launched in the next year, and they will carry a new retroreflector panel. This brings me to my conclusions. First is the LRS support. LRS is providing around 100 to 300 normal points per day. Campaigns are increasing this amount. And on the result side, for the optical cross section, we see that there are more normal points for IOB than for fog. This is linked to the optical cross-section. And for the normal point accuracy and precision from the this is normally derived from orbit residuals, but they include the orbit accuracy. The orbit accuracy for Galileo has been improving since 2011 to nowadays. At the moment, is at the level of 1 centimeter with the latest model. But further model improvements are not clearly visible on the SLR residuals based on 3 days fittings. We have to do longer fittings to see the benefit of the model, and to do further refinement to try to break this 1 centimeter level and bring it to the 1 millimeter. For that, we are looking into the new Tenerife Isania station that is providing a very good initial performance and doing single difference to other stations to get better knowledge on the normal point performance without orbit contribution, and also looking to alternative normal point formation as mentioned by Michael this morning. Then there is a new satellites under production and new satellites ready to be launched. And finally, I want to thank LRS for the support for the Galileo mission. In particular, the all-orbit model improvement that has been achieved has been done thanks to the SLR data, and this has led to the contribution of Galileo to the IDRF 2020, as highlighted yesterday in different presentations, in particular regarding the scale. That concludes my presentation, and I will be happy to answer questions.
Thank you. We have a couple of questions online. We'll take first. The first one is, which empirical orbit parameters are estimated in the ECOM light model?
It is a reduction of if I remember, it was 5 parameters. It was D, Y, and B plus D sinus and D cosinus. Then it was reducing the number of parameters and trying to use better the a priori information.
Okay, and then there's 2 other questions here. Which are the physical basis of your thermal model? And the other question is, yep, more questions keep coming. Let's start with just that one. Which are the physical basis of your thermal model?
The physical basis of the thermal model is basically the thermal readings from the satellite. We have used between the plus minus Y of the satellite. You have thermistors all around the satellite. We have used these values to compute what is the thermal thrust and convert that into watts. The basic physics of the model are thermal readings on the satellite.
Maybe before we take those, we can see if anybody in the room has a question they want to jump in.
Hello, Francisco. Thank you for your talk. I'm wondering whether you can tell us how big or how large the optical cross-section of the second generation Galileo will be compared to the first generation.
Compared to the IOB generation, to the fog generation, I can tell you that is larger, but I cannot give you the exact value. I can tell you that it will be aligned with the recommendation from ILRS for tracking GNSS satellites.
Do you know the size and the number of cubes?
Size of the number of cubes is under the definition, but it will lead to an optical cross-section that is aligned with the recommendation from ILRS.
Okay, so 100 million square
meters. At this moment, there are 2 satellites under definition. Unfortunately, I cannot tell you anymore.
Okay, thanks. Any questions from the room? If not, we'll jump quickly. When new metadata will be released by ESA, optical properties in particular?
Yeah, this release process goes through the Galileo Service Center. At ESA's design authority, what we have done in the last year is to collect this information, to validate it with the help of ESOC, and this information is now ready for publication. Then we expect that in the next months, this information will be released through the Galileo Service Center website. But from our side, the information is ready to be published and fully validated.
Great. One final quick question here. Is 1 centimeter orbit accuracy 3D or radial?
Sorry, can you repeat the question?
Is the orbit accuracy three-dimensional or radial?
Three-dimensional.
Okay. Great.